So we now move on to section 3.2 about equivalence of norms. Now, in order to discuss this properly, we do need to remember the notion of equivalent metrics and uniformly equivalent metrics. Equivalent metrics we discussed in our revision session. Is there anyone who needs reminding about equivalent metrics? It was the two metrics that give the same topology, two metrics that would give the same sequences with the same limits. Oh, okay, you already had the same sequences. The same convergent sequences with the same limits. And more sophisticated approach that the identity map was a homeomorphism from the set to itself when given the two metrics. So you have two different possible metric spaces, and you say the metrics are equivalent if they give the same topology, if the identity map in that setting is a homeomorphism, continuous in both directions. Uniformly equivalent is a bit more problematic because not everybody uses the same terminology, it turns out. So I want to warn you, if you want to look in Sutherland's book on metric and topological spaces, which is highly recommended, this is on metric and topological spaces. It's the book of Sutherland. An introduction to metric and topological spaces. And there, the terminology there, what I call uniformly equivalent, he calls Lipschitz equivalent. And unfortunately, he uses uniformly equivalent for something else. I'm not alone. Other people have used uniformly equivalent for this. I have to say that I think Sutherland's terminology is more logical. And so I do have a feeling that it might be a good one to move to. So Sutherland uses Lipschitz equivalent for our uniformly equivalent. And he uses uniformly equivalent for something else. Oops, come back. There we go. So Lipschitz equivalent is logical. It means that identity map, rather than just being continuous in both directions, is Lipschitz continuous in both directions, meaning there's some Lipschitz constant showing that the two metrics are within constant multiples of each other. Not that they are constant multiples of each other, but there's some inequalities. So this is that d1 of xy is smaller or equal to c1 d2 of xy, and d2 of xy is less than to another constant times d1 of xy. That's what I call uniformly equivalent, or did, and more logically what Sutherland calls Lipschitz equivalent, because there is another notion of uniform equivalence which makes more sense, which is that the identity map should be uniformly continuous in both directions. And that lies in between. That lies strictly in between the notion of equivalence and Lipschitz equivalence. And on the other hand, I don't know of any good use for that intermediate notion. I've never come across a use for that intermediate notion. I've only ever wanted to use either equivalence, topological equivalence, or the strongest Lipschitz equivalence with constants. Actually, there's an even stronger one, of course, being isometric. If the two metric spaces are isometric, then you've actually got Lipschitz equivalence, but with the Lipschitz constant 1 in both directions, which is a particularly strong version of Lipschitz equivalence. Right. But now we're talking about norms instead of metrics. So we say they're equivalent norms if they induce equivalent metrics. Well, that's sort of obvious. But a surprising thing happens with norms. With norms, all the different notions of equivalence agree, unlike with metrics. Okay, so this is not obvious at all, but unfortunately I'm going to be leaving some of this as an exercise. However, it's very similar to something I'm going to do in more detail later. So what's going on here? The official definition of equivalent, then, is that the norms give you the same topology, same convergent sequences, same limits, that the identity map is continuous in both directions. And from when we come back and look at linear maps in both directions, linear maps later in the next section, and I do some of this stuff in more detail, then you will see how to do any of the details that I've left out on some of these exercises. So metrics might be equivalent without being uniformly equivalent, or Lipschitz equivalent, whichever term you want to use. But for norms, it's not true. The following are equivalent. So the norms should be equivalent. Each norm is less equal to some constant times the other norm. And that's pretty much the same as, given that you know how the distances and the norms are related, that's pretty much the same as saying that they're Lipschitz equivalent, which is what we're calling uniformly equivalent. Lipschitz equivalent if you're using terminology from Sutherland. I guess in some sense we're fortunate because uniform equivalence fits in the middle, and since all of these are equivalent, they're also going to be equivalent to uniformly equivalent for the Sutherland version when you're dealing with norms. So all the different notions of equivalent are equivalent for norms. And then you get the nice thing about this uniform equivalence or Lipschitz equivalence is that unlike the ordinary equivalence of metrics, uniform equivalence or Lipschitz equivalence does preserve completeness. If you've got two metrics that are uniformly equivalent within constant multiples of each other like this, and one is complete, then the other one is as well. The reason being that Cauchy sequences, the notion of Cauchy does get preserved if you've got these constant bounds. So these constants help you to preserve Cauchy. So Cauchy sequences are the same for both norms, and of course, if they're equivalent, then convergence and limits are the same for both norms, and as a result, completeness will be the same for both norms. So equivalent norms, if one's complete, the other one's complete, which is very different from the situation for metrics, where we know, for example, on the open interval 0, 1, you could put two different metrics, one of which is complete and another one which isn't, but both giving the usual topology. I wonder, though, whether you might want to see some details of that. Perhaps I should say something. Let's have a look. Let me indicate some connection between A and B. B implies A is rather easy. If you've got these constant bounds on each other, it's very easy to check that you're getting Lipschitz continuity in both directions, and so your identity map is continuous in both directions, and you get equivalence. So B implies A is very easy. So let me have a look at not B implies not A. So I'm going to give you some details. So in the above, B implies A is easy. You should check the details. Let's do not B implies not A. Let's suppose, given that B is false, then one of those constants doesn't exist. So either C1 or C2 doesn't exist. And it's symmetrical, so given B fails, either one of these constants C1 and C2 doesn't exist. Without loss of generality, there's no constant C1 with the desired property above. So without loss of generality, that's WLOG, no such constant C1 exists, satisfying the conditions of B. So that means that for every C1 greater than 0, that condition fails. So for all C1 greater than 0, there must exist an X in E showing that it fails. Norm x1 being strictly greater than C1 norm x2. So all I've done is I've negated things and explained what's going on. So let's call this star. If it was C2 that was missing, the same proof works, or you can argue by symmetry. That's why I said without loss of generality, it's a C1 that goes wrong. Okay, now we apply this with C1 equals 1, 2, 3, 4, and so on. And that means we can choose a sequence xn in E with norm xn1 greater than n norm xn2 for all natural numbers n, and we do that by applying star with where's it gone? Applying star with C1 equals n. So we do it once for every natural number, and that means we get a sequence. Inductive choice, I suppose. Or sequential choice, perhaps, is what I mean there. Anyway, or countable choice. Never mind. Now, what can you tell me about xn? Not very much, of course, but you can tell me something about xn. There's very little you can tell me about xn, so can anybody see anything you can tell me about xn? That's true. So they're coming from a smaller and smaller choice of set. But okay, I don't think that one's going to help us though. But can you tell me anything that xn definitely isn't? Yeah, is not the zero vector. The norm of the zero vector is 0, and then you'd have equality. I've got strict inequality here. That's convenient. It saves me a tiny bit of time. So let me note. Note that xn is not 0. That's going to be convenient because it means we can divide by its norm. We can divide by either norm, and we won't be dividing by 0. So let me divide by the norm xn1. So we'll set yn equals 1 over the first norm of xn times xn. This is a standard trick for normalizing things, which is, of course, in E. Then norm yn 1 is 1, okay? But norm yn 2, what can you tell me about norm yn 2? If we go back and look at that equation here, the 1 norm is greater than n times the 2 norm. The norm yn2 is less than 1 over n. Yeah, that's the one. So now let's have a look at this sequence. Who can tell me something about convergence? Convergence and lack of convergence. In what sense does yn converge to something? Okay, so with respect to norm 2, this sequence converges to 0. What about respect to norm 1? With respect to norm 1, all of the terms have got norm 1, and so the limit can't be 0. It doesn't have to converge to anything, as far as we know. So it definitely doesn't tend to 0 with respect to norm 1. So we've got a sequence that converges to 0 with respect to one norm, and not with respect to the other, so they're not equivalent. That's not the only way to do it, by the way. But that's an approach using sequences that's not too bad to work with. So, and that was the hard part. So note, that was the contrapositive of equivalence implying Lipschitz equivalence. So you get the easy bit right round now. So now you've got equivalence implies equivalence with constants, which is the least obvious of these facts. So the rest of the exercise is relatively easy. Any questions about that? If not, we shall move on. To our big theorem 3.8. This is a very nice result. Take any given finite dimensional vector space, all norms on it are equivalent to each other, and they're all complete. And they all satisfy they've all got the Heine-Borel theorem works in all finite dimensional norm spaces, and the Boltzmann-Weierstrass theorem is true in all finite dimensional norm spaces, and sort of everything. And this is an amazing bootstrap operation, where you start by using what you know about the ordinary Euclidean space, and then use that fact that you already know about that to prove that all the other ones are essentially the same, from which you get that they've all got the same nice properties too. So you have to make sure you're not circular. So you mustn't assume that these other norm spaces have got all the nice properties that norm 2 has, the Euclidean norm, in order to try and prove that they have. But what's amazing is that you end up with an inequality one way round, and you use it to prove an inequality the other way round. And it's rather unusual to be able to deduce, you might think it's unusual to be able to use sort of an inequality one way round to prove the inequality the other way round, but it's actually quite a common feature in functional analysis. So let me tell you then the sort of things we're going to need in this proof of theorem 3.8. We're going to assume we'll use the completeness of f to the n with norm 2, that's Euclidean norm. Which, of course, we proved earlier. Remember, that's f equals r or c. And I sketched a proof for you that you were complete with the Euclidean norm, where we used our usual Boltzmann-Weierstrass theorem, which is valid in n-dimensional Euclidean space. And that's our main tool. We also will use Boltzmann-Weierstrass or Heine-Borel theorem. You can use either one in this space. So we also use Heine-Borel or Boltzmann-Weierstrass in that space. You can do it either way. We know that f to the n, if it's r to the n, it's r to the n, we know all about it. If it's c to the n, then it's really r to the 2n as a metric space, and we know all about that. And we know that the Heine-Borel theorem is true, so you're closed and bounded if and only if you're compact or sequentially compact. If you're, Boltzmann-Weierstrass again, bounded sequences have got convergent subsequences. So either way, that works when we're working in the usual norm, the usual Euclidean norm on f to the n. So what we're going to do is we're going to put some random norm on it, well, it's essentially we're putting a random norm on f to the n and checking that things still work there. Now, before I give you the proof, let me have a quick look at this corollary here. Every finite dimensional subspace of a norm space is closed. Now, where does that come from? Can anyone see how that works? You take any old norm space, probably infinite dimensional. It doesn't have to be a Banach space. Then you take a finite dimensional subspace of it, and you restrict the norm to it. What happens? It must be complete, because finite dimensional norm spaces are always complete, and every complete subset of a metric space is closed. So finite dimensional subspaces of norm spaces are automatically closed. Doesn't matter how incomplete the norm on the big space is. When you restrict it to a finite dimensional subspace, it becomes a complete norm, which forces that subspace to be closed, because complete subsets of metric spaces are closed. A remarkable fact. It's actually true in more generality in topological vector spaces, but I don't want to get into that. If you're interested in topological vector spaces without metrics, you should go and look at Rudin functional analysis. But that, I have to warn you, is quite a tricky book. So topological vector spaces, as in Rudin's book, Functional Analysis. But it's a tricky book. More advanced. And now you can use that together with the closed sets version of the Bayer category theorem, which is what I wanted you to use in order to answer the question sheet question that I'm still waiting for people to hand in, to show that you can't have a countably infinite dimensional Banach space. I want you to think about that for a bit longer before I come back and show you how that one works. What I want to do now is prove theorem 3.10. 3.8. Obviously, I'm not going to get very far today, so let me just give a preliminary discussion of what we're going to be doing. Okay, so there's a preliminary discussion. We've already mentioned the properties we're going to need. So we're going to be, as I said, f to the n with Euclidean norm, norm 2. We have the standard properties of that. Now, if you've got just any old n-dimensional vector space, it's always isomorphic to f to the n. So it could be real or complex. So let E be, I'll use M actually, because I got into trouble in the past by using n, and I don't like using up n. So let's say E is an m-dimensional vector space over F. Zero-dimensional is not very exciting. We'll assume that m is greater than 0. Else it's trivial. Then E is isomorphic to f to the m. But let's be a bit more specific. So it's not very specific. More specifically, if you let v1, v2 up to vm be a basis of your space, then you can define an isomorphism it's a linear isomorphism T from f to the m goes to E by T of, you need some scalars, lambda 1 up to lambda m, is lambda 1 v1 plus lambda m vm. And of course, to say that v1 up to vm is a basis is to say that this is a linear isomorphism between f to the m and d. So that's all we're really saying. The inverse map is quite interesting. The inverse, theta minus 1, from E goes to f to the m, gives you coordinate vectors. For each point of E. That is, so for each x in E, there are unique lambda 1 up to lambda m with scalars, of course, with x equals sum from k equals 1 up to m of lambda k vk. And then theta minus 1 of x is lambda 1 up to lambda m, is the coordinate vector for x with respect to this basis. I guess with respect to the ordered basis. V1 up to Vm. So as long as you decide which order you're going to have your basis elements in, then you get this nice notion of a coordinate vector corresponding to ordered basis and so on. And this is pretty standard linear map theory. Now, so this means that you can pull across the Euclidean norm from F to the M to E to define a norm on E which makes it isometric to Euclidean space. And so that's one particular norm you can use on it. And if you use that norm on E, then it's got all the nice properties we know. It's got the Heine-Borel theorem, it's got Boltzmann-Weierstrass and all that. So there is at least one really nice norm we can put on E. And our task is to show that any other norm you put on E is equivalent to that one. And that's what we're going to do next time. Okay, better stop there.